When Concorde first took flight in 1969, it became a symbol of what modern aviation was capable of, traveling across oceans in a matter of hours. However, the dream of supersonic transport turned out to be a deafening one for humanity, like literally. Thunderous sonic booms made it impossible to fly these aircraft over densely populated areas, and so Concorde disappeared from the airspace after 3 decades. Today, NASA and Lockheed Martin have promised to bring back supersonic flights, making them virtually silent. So let's check out their X-59 QueSST project and see how it's doing. In October 1947, General Charles "Chuck" Yeager officially ushered in the era of manned supersonic flight by breaking the sound barrier for the first time at the controls of the pioneering experimental X-plane, the Bell X-1, coming in at Mach 1.07. At the end of December 1968, after decades of testing, things finally came around with the hastily completed first flight of the world's first commercial supersonic transport aircraft, the Tupolev Tu-144. With all its might, it sought to outrun its overseas competitor, the British-French passenger Concorde, whose first flight took place in early March 1969. As a result, the Tu-144 encountered many problems while in passenger service from 1977 to 1978, having completed only 55 flights along only one route. Concorde was actively used from 1976 to 2003, but then fell victim to its own gluttony, namely high fuel consumption associated with the need for high traction, excessive operating costs, and as a result, expensive tickets, as well as the impact of sonic booms on the environment. The 1973 FAA ban on supersonic flight over cities severely limited the routes suitable for the Concorde, seriously and permanently discouraging engineers from developing new supersonic civil aircraft. There were some pluses, though, too. Despite the tragic death of the ambitious apparatus, the phenomenon of sonic boom continued to arouse genuine interest among scientists around the world. Therefore, over the ensuing decades, they spent tens of thousands of hours and millions of dollars in research aimed at understanding this phenomenon, as well as predicting it. In fact, a sonic boom is akin to thunder, a sharp sound clearly audible to people on the ground when a plane flies past the speed of sound. This noise can be so loud that it's quite capable of damaging structures or ground transportation. When, for example, a space shuttle accelerates to high speeds, it creates ripples of air molecules and sound that spread out in all directions, like a pebble you throw into a lake. As this shuttle accelerates, the waves in its bow begin to accumulate and compress rather than spreading outward. Meanwhile, waves of air and sound continue to bounce off the sides and back of the ship, like the wake of a speedboat cutting through the water. If the speed of the shuttle continues to increase, it'll eventually exceed the speed at which the waves in front of it are traveling, that is, exceed the speed of sound, which is 760.5 miles per hour, or Mach 1. At this point, so much pressure is built up in the front of the craft that it releases a huge sound wave, also known as a shock wave, which sounds like an explosion. It's this sharp release of pressure that we hear on the ground. Its intensity and distribution on the ground primarily depend on the weight and dimensions of the aircraft, the altitude at which it flies, and also its speed. The area affected by the sonic boom is called the boom carpet and can extend up to 70 miles behind the aircraft. Mitigating sonic boom has been, is, and still remains a full-blown headache for everyone involved in supersonic flight. Since the 1950s, billions of liters of coffee have been drunk in an attempt to understand this phenomenon and accurately model it. Sonic boom prediction is, in fact, a fundamental requirement for both the design of advanced supersonic transport and environmental assessment tools for various military and aerospace activities. The best method to date for minimizing sonic boom is considered to be that of Robert T. Jones and Harold W. Carlson, who stated that sonic boom can be greatly reduced by careful design of the fuselage and wings of the aircraft. Simply put, if you change the form, you'll change the consequences. This idea was picked up by NASA, which tested its Quiet Spike, a telescopic rod mounted on the nose of an aircraft to weaken the force of shock waves generated at supersonic speeds, and then moved on to work on a full-fledged aircraft, the X-59 QueSST, or Quiet Supersonic Technology. Of course, almost no ambitious experimental aircraft could beat the team of specialists at the Skunk Works, a division of Lockheed Martin that's worked on dozens of the most secret U.S. aircraft developments. They quickly joined NASA's low-boom flight demonstrator project in an effort to bring supersonic flight back to civil aviation. Yes, the X-59 is not a commercial airliner prototype and will not be able to carry passengers on its own. But what's at the forefront here is its quiet supersonic technology, which is expected to be adopted by aircraft manufacturers around the globe in the future. QueSST was largely developed as a result of a preliminary design contract awarded to Lockheed back in 2016. Granted, at that time, no one suspected the coming pandemic and the subsequent forced shift in the schedule of plans for the first launch, but this doesn't necessarily mean the engineers wasted their time. In the winter and spring of 2017, they actively tested a 9% scale model of the future aircraft in a wind tunnel at speeds from Mach 0.3 to 1.6, intending to prepare a preliminary review of the project by the summer of that year. In 2018, NASA signed a $247.5 million contract with Lockheed Martin for the design, construction, and delivery of an experimental aircraft, which was then better known as the low-boom X-plane. Afterwards, work began to boil with renewed vigor, and by the summer of 2018, it was given the designation X-59 QueSST. In the fall of 2018, NASA Langley Research Center completed another wind tunnel test, but with an 8% scale model with high angles of attack of up to 50 and 88 degrees at low speeds. Previous tests had been supplemented with an impressive amount of new data on static stability of the X-59 and its controllability. Assembly started in June 2019, but by the end of 2020, construction was only half completed. By November of 2022, NASA reported the installation of a General Electric F414 GE100 engine with a thrust of 22,000 pound-feet, 98 kilonewtons, at the Skunk Works plant in Palmdale, California. The GE F414 will allow the aircraft to reach speeds of up to Mach 1.5 or 990 miles per hour with a cruise speed of Mach 1.42 or 940 miles per hour at an altitude of 55,000 feet. The Concorde, with its Mach 2 and 60,000 feet altitude, was more powerful, but the fuel consumption and noise were quite something. The result of the Herculean effort by the NASA and Lockheed team was a craft that measures nearly 100 feet in length, the lion's share of which is its sharp nose with a wingspan of 29.5 feet and a maximum takeoff weight of 32,300 pounds. The first thing that immediately catches the eye is the shape of the aircraft. This was, of course, designed that way for a reason. In a typical aircraft design, shock waves begin to accumulate behind when it reaches transonic speeds, close to the speed of sound. In the case of the X-59, the overall shape with its long, narrow airframe, sharp nose, and canards will keep shock waves from converging, thereby significantly reducing the craft's acoustic signature as it travels at supersonic speeds. That is, instead of strong shock waves combined into a loud hum, weaker shock waves will be heard as a rapid series of soft thumps. Although in reality, NASA and Lockheed strive to ensure that the noise created by their aircraft ultimately does not exceed the volume of closing a car door, which is about 75 effective perceived noise decibels, versus the 110 effective perceived noise decibels for the same Concorde. But if rather than using aviation measurements, we instead translate this into a figure more familiar to us, it'd be about 60 decibels. Due to the experimental nature of the device, the creators could not afford unnecessary squandering. In an effort to keep the design as simple and inexpensive as possible, Skunk Works borrowed the chassis from the U.S. Air Force General Dynamics F-16 Fighting Falcon. QueSST got the cockpit canopy from the NASA Northrop T-38 Talon training aircraft. Part of the propulsion system was taken from the Lockheed U-2 Dragon Lady reconnaissance aircraft, and the F-117 Nighthawk stealth fighter, which also once appeared from under the wing of Lockheed, generously shared its control stick with the new device. In total, according to the team, only 10% of the design components are actually new, which is why some even jokingly nicknamed the X-59 Frankenplane. On the other hand, this did not stop Lockheed from taking a new manufacturing approach when designing the QueSST. The aircraft was used to test advanced manufacturing technologies, such as large one-piece composite skins on the wings. X-59 was the first Skunk Works project to use new high-tolerance and highly automated robotic drilling and tapping capabilities. Another striking feature of the design is the complete absence of any line of sight for the pilot. The cockpit uses the External Vision System, or XVS, which allows the pilot to see via the feeds from an array of forward-facing high-resolution cameras. Complementing its capabilities is the Collins EVS 3600 multispectral imaging system located under the QueSST nose, which is used for landing. In January 2024, NASA and Lockheed officially unveiled their supersonic test aircraft with a launch ceremony at Plant 42 Skunk Works in Palmdale, and almost a year later, in December 2024, NASA successfully completed the first test of the engine with maximum afterburner, which was the next important step forward in preparing the device for flight. These integrated tests are to figure out whether the aircraft systems will operate correctly using power from its own engine. During the first set of tests, the engine was rotated at a relatively low speed without ignition to check for leakage and ensure that all systems communicate as expected. The team then fueled the X-59 and tested the engine at low power, and later ran it at high power with rapid throttle changes to simulate real flight conditions. Now both NASA and Lockheed are looking forward to the first flight of the X-59 planned for this year. Some might rightfully be indignant at the shift in plans for almost 5 years, but on the other hand, you don't want to rush things when it comes to a potential revolution in passenger transportation, even if, in some sense, it's based on a repeat of the Concorde's success. What do you think? Will Quest help speed up the mass adoption of supersonic transportation? Or is it still too early for us to dream of traveling from Paris to New York in a mere couple of hours? Be sure to share your thoughts in the comments below. And if you enjoyed the video, please leave a like, subscribe to the channel, and hit that notification bell for more content like today's. Thanks for watching, and we'll see you in the next one.